Hey guys, welcome to your next lesson. Today we're going to talk about convergence of a sequence. Now, most of the time, what we're concerned about is convergence of series. So we're going to spend almost all of our time devoted to that. But we do want to talk about convergence of a sequence. It's a little bit different. So we'll start with this. It says write the first four terms of each sequence given the general term. So these are sequences, so it's just a list of terms as opposed to the sum of a whole bunch of terms. It's a list of a whole bunch of terms. And we'll think of these as an infinite list of terms, but these are going to be sequences. So we want to write the first four terms of each of these. Okay. So notice here it says n equals 1, comma 2, comma 3. So that's just to tell you that we're starting at n equals 1, because you don't always start at n equals 1. We could have started at n equals 0, or maybe even some other value of n. But we're going to start at 1 for each of these and just keep indexing upwards from there. Okay, so let's take a look at the first one. It's a sub n. This is the general term for the sequence. It's 3n squared plus 1 over n squared. So we start with n equals 1. You plug in 1. The numerator is 4. The denominator is 1. So the first term of this sequence is 4. The next term, we plug in 2. So that's going to be, what, 12 plus 1. That's 13 over 4, I guess. It's plugging in 2. So it's just a list of numbers. It's a sequence. Plug in 3. So now we have 9, so that's 27 plus 1, so that's 28 over 3 squared. So that's 28 over 9. That's the first three terms. We'll get one more, we plug in 4. So that's 16, that's 48 plus 1, so that's 49 in the numerator. 4 squared in the denominator, so that's 49 over 16. And we can envision this sequence going on forever, this list of numbers. So we're not adding anything together, we just have this list, this sequence of numbers. Okay, the next one. B sub n equals e to the n. So that's the general term. So b sub 1 would be the first term of the series, and that would be e to the first. B sub 2 would be e squared. B sub 2 is the second term of the series. B sub 3 would be the third term of the series. That's e cubed. The fourth term would be e to the fourth. And then this one goes on. The next one, we have c sub n. Our general term is 2 over 4n squared minus 1. So our first term of the series, we plug in 1. So we have 4 minus 1. So the first term of this series, I think I said series. I meant to say sequence. These are sequences here. Sorry about that. So we have 2/3 is the first term of the sequence. The next term of the sequence, we plug in 2. So that's 4, 16 minus 1. So it looks like 2 over 15 is the next term in this sequence. We plug in 3 next, and we have 2 over, 36 minus 1? 2/35. The fourth term of the sequence, we're now up to n equals 4. So c sub 4, that's your fourth term, is 2 over 64 minus 1, I guess. So 2 over 63. Dot, dot, dot. All right, so these are sequences. And we want to talk about the convergence of these sequences. Okay, so if we just look at the numbers, if we're looking at a convergence of a sequence, we're like, well, is the sequence of numbers approaching a number, right? So we got 4 here. We have what here? This is 3 and a fourth. So we're getting a little smaller, I guess. And then this is 3 and 1/9. This is 3 and 1/16. So it looks like we're getting closer and closer to 3 here. I don't know. Here, of course, the numbers are just blowing up. And here, the numbers are getting smaller, 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 and maybe, I don't know, approaching 0 maybe? I don't know. But that's what we're talking about with the convergence of a sequence. So if this is the first term, a sub 1, the a sub 2 term, the a sub 3 term, the a sub 4 term, what we're really looking for is the a sub infinity term, I guess, which really involves a limit, right? So the question is, which which of these sequences converge? So which of these sequences converge? And again, to know the answer to that, we're looking for that a sub infinity, this a sub infinitieth term. Okay, so here, what we're looking for is really this, the limit as n goes to infinity of a sub n. So we're analyzing this one here. That's the getting to that infinitieth term. So this is the limit as n goes to infinity of this, 3n squared plus 1 over n squared. All right, so we're getting used to this now, I think. So when you're going to infinity and you have polynomials like this, numerator and denominator, you look at the degree. The degree is the same. So this limit, since we're going to infinity, is going to be the ratio of these coefficients, 3 over 1. So this is 3. And we had said that these numbers looked like they were approaching 3. And this sequence does indeed converge to 3. So this converges to 3. So this one here converges, and it converges to 3. Okay. The next sequence, again, we want to do the same thing. That's the b sub 1 term, the b sub 2 term. We want the b sub infinity term. So we have to really look at it as a limit as n goes to infinity of b sub n. So that's the limit as n goes to infinity of e to the n. And of course, this is infinity. We knew that this one was blowing up, right? So this one clearly does not converge. This sequence diverges. Our third sequence, so we have the c sub 1 term, the c sub 2 term, the c sub 3 term, the c sub 4 term. We want the c sub infinity term. So we'll do the limit as n goes to infinity of c sub n. So we have here the limit as n goes to infinity of 2 over 4n squared minus 1. As n goes to infinity, the denominator is blowing up relative to the numerator. So this is approaching 0. So this one also converges, and in this case, converges to 0, which we kind of said it might, right? Because we saw what these numbers were kind of doing, getting smaller and smaller, perhaps approaching 0, and we've just confirmed it that, yes, indeed, that sequence converges to 0. So 2 of these 3 converge. This one converged to 3. This one diverged, but this one converged to 0. Okay. You don't have to copy this because it's just capturing what we have on the other side of the board, because we jump right to this. What does this tell us about each series? Okay, so we know how to tell whether a sequence converges now, but what does this tell us about each series? The sum from n equals 1 to infinity of a sub n, the sum from n equals 1 to infinity of p sub n, and the sum from n equals 1 to infinity of c sub n. So remember, this one converges to 3. The sequence converges to 3. This sequence diverges. This sequence converges to 0. So since this sequence converges to 3, what would the series do? Now the series is what? Well, the series is the same numbers, but of course we're adding them together. 4 plus 13 fourths plus 28 ninths plus 49 over 16 plus, and we keep adding them up until we get to infinity, I guess, right? Okay, what do we think that does? So the sequence converges to 3. And what that really means is the final term, whether we're talking about the sequence or the series, is 3. And we learned yesterday about that nth term test for divergence. And in order to have a series that's a candidate for convergence, we need to have that final term approach 0. It does not do that here. It approaches 3. So the sequence converges, but the series diverges. So if we take a look at this series diverges. And it diverges by the nth term test, specifically the nth term test for divergence. Because remember, the nth term test for divergence, we're taking a look at that all-elusive final term, and that's basically what we did when we were looking at this, right? That all-elusive final term is 3. That's not 0. So the series has no chance of convergence. So the series diverges. The sequence converges to 3, but the series diverges. In the B, we have the sequence that diverges. Well, of course, the series will also diverge in that case, because we're not getting that final term being 0, of course. So this is a divergent series, again, also by the nth term test. But what does the convergence to 0 for the sequence in C sub n tell us about this series right here? Okay, so this one, the sequence converges to 0. And again, what that means is, if I look at this as a series, 2/3 plus 2/15 plus 2/35, 2 over 35 plus 2/63 plus dot, 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 the final term I'm adding is 0. And that means we have potential for convergence. It doesn't mean it definitely converges. It means we have potential for convergence. So this maybe converges, because by the nth term test, that all-elusive final term of this series is 0. So the sequence converges to 0, and that means the series has a chance to converge. If the sequence converges to some number that's not 0, then it doesn't have a chance to converge. It diverges. That's really the nth term test for series. So that's the connection between sequences and series in terms of convergence. But we're still curious to know, what does this series do? This one right here. So the sum from n equals 1 to infinity of 2 over 4n squared minus 1. So that's what we're going to explore next. Okay, so of the 3 series we were looking at, based on those sequences we were looking at, only one of them had a chance to converge. So even though 2 of the sequences converged, one of them converged to 3, which basically means when you write it as a series, that final term is 3. So in order for a series to have a chance to converge, that final term needs to be 0, which it was for this. So this has a chance to converge, this series right here. So let's explore it. Let's see if it does actually converge, or perhaps maybe it diverges. Let's take a look. So what we're looking at really is the sum from n equals 1 to infinity of the general term 2 over 4n squared minus 1. Now, one thing you might remember is that one way we can analyze the series is by looking at this very special sequence called a sequence of partial sums. And if you recall, if the sequence of partial sums converges, that means the series that generated it also converges. So let's look at it. So we're going to look at the sequence of partial sums. Now, we've done this before, so you probably remember this. Okay, first, let's take a look at what the series actually is. So the series is, well, I know because I plugged in 1 into all of these to build the sequence. So the series is simply 2/3 plus 2 over 15 plus 2 over 35 plus 2 over 63 plus ... So the sequence of partial sums is this. The first term of your sequence of partial sums is the first term, but the second term of your partial sum, of your sequence of partial sums, is going to be the sum of the first 2 terms. So that's 2/3 plus 2/15. All right, we can do this, right? Common denominator 15, so that's 10/15. There's your 2/3 right there, plus 2/15. So that's 12/15. So it looks like this turns out to be what, 4/5. Okay, so that's the second term in the sequence of partial sums, 4/5. The third term in the sequence of partial sums is the sum of the first 3 terms. So we're going to add those 3 fractions together. Well, I've already added the first 2 together, so I'm just going to add 4/5 to that third term, 2 over 35. Common denominator, 35. So there's your 4/5 right there. We'll add that to 2/35, and we get 30 over 35, which is the same as 6/7. The fourth term in the sequence of partial sums is the sum of the first 4 terms. Well, we've already added up the first 3, that's 6/7. So I'll add the fourth term, which is 2 over 63. Common denominator is 63. So this would be 54 over 63. There's your 6/7 right there, plus 2 over 63. So we have 56 over 63, and that is what, 8 over 9? So my sequence of partial sums looks like this. First term, 2/3. It's a sequence, right? So the second term in my sequence, 4/5. The third term in my sequence of partial sums, 6/7. The next term in my sequence of partial sums, 8/9. And then on and on and on. It looks like they're approaching 1, I don't know, maybe. But we can figure out what it's approaching if we can get a general term for the sequence, which is pretty easy here, actually, because let's see if we can get that general term. We'll sneak it into our sequence here. If we consider this n is 1, here n is 2, here n is 3, here n is 4, well, clearly the numerator is nothing more than just 2n. So 2n will be the numerator of my general term. Now, the denominator is 1 more than the numerator. So there you go, 2n plus 1. So this is the general term for my sequence of partial sums. Okay, so does this sequence of partial sums converge? Well, this is the a sub 1 term. I guess we can think of it that way. Oh no, let's call it s sub 1 since it's a special sequence of partial sums. That's my s sub 1. There's my s sub 2. There's s sub 3. There's s sub 4. This, of course, is s sub n. So s sub n is the general term in my sequence of partial sums. And that's 2n over 2n plus 1. But which term would we like to see? Well, I guess the last term of that sequence to see if the sequence converges. So that would be the limit as n goes to infinity of s sub n. In other words, the limit as n goes to infinity of 2n over 2n plus 1. Okay, since we're going to infinity, and these are polynomials, we'll look at the degree on the top and bottom. And they're the same, they're both degree 1. So it's the ratio of the coefficients, so we know this is equal to 1. So our sequence of partial sums converges, so that means this series does too. So we write it. Since the, and we'll abbreviate it here, sequence of partial sums converges, the series, which is this series, the sum from n equals 1 to infinity of 2 over 4n squared minus 1 also converges. And not only that, we know what the series converges to. The sum from n equals 1 to infinity of our series 2 over 4n squared minus 1. What's it equal to? Well, think about it. We're looking at a sequence of partial sums, right? So this 2/3, of course, is the first term of the series. The second term of the sequence is the sum of the first 2 terms of the series. The third term is the sum of the first 3 terms of the sequence, or the series, sorry. The fourth term is the sum of the first 4 terms. So the final term would literally be the sum of all the terms. In other words, the value of the series. And we just said that that limit, that infinitieth term of the sequence of partial sums was 1, so the value of the series is 1. So it converges, and not only does it converge, it converges to this. Okay, we're going to take a look at the same series, but we're going to take another approach. It's also going to involve a sequence of partial sums, but we're going to do it in a slightly different way this time. So one of the things we recognize about this fraction, 2 over 4n squared minus 1, is that we can algebraically manipulate it. The denominator is clearly factorable. So this is 2 over 2n plus 1 times 2n minus 1. And one thing I could do with that is I could write this 2 over 2n plus 1 times 2n minus 1 as a sum of partial fractions. So let's do it. Of course, we're going to take the whole equation and multiply it by the same thing. So that same thing is going to be this, 2n plus 1 times 2n minus 1. That's going to multiply the entire left and the entire right. Here, this cancels with this, I got 2. 2n plus 1 cancels with this, I have a times 2n minus 1. Plus 2n minus 1 cancels with that, so I have b times 2n plus 1. All right, so let's do a little distributing here on the right. So we have 2an minus a plus 2bn plus b. If I do a little rearranging here on the right, I could say I have 2a plus 2b times n. That takes care of these two. And then I have minus a plus b. So now we do that matching game. What's the coefficient of n here on the left? 0. So that means that 2a plus 2b has to be 0. And this constant, negative a plus b, has to match this constant over here. So negative a plus b is 2. Okay, here, I don't know, 2a equals negative 2b. So yeah, a is equal to negative b here. So that means I guess I can plug in negative b into this a. So negative b plus b is equal to 2. So 2b equals 2. B is 1. And if b is 1, a is negative 1. So what this means is I could rewrite my series now. The sum from n equals 1 to infinity, I can rewrite this term. And that term can be the sum of two fractions. Notice b is positive 1, so I'm going to write that one first. 1 over 2n minus 1. A is negative 1, so I'll write that one second as a subtraction, right? So minus 1 over 2n plus 1. So this is an equivalent way of writing the same series here. And now let's take a look at the sequence of partial sums, now that we've written it as a pair or a sum of partial fractions. Let's take a look. Okay, so let's take a look at the series as it looks now, presented like this. So we're going to plug in 1 first. This is one term. This whole thing is one term, right? So I'm going to plug in 1 for n here and here. When I plug in 1 for n here, that's going to be 1 over 2 minus 1. That's 1. So my first term is going to be 1 minus whatever this turns out to be. So I plug in 1 here. That's going to be 1/3. So there's your first term right there, 1 minus 1/3. The next term in the series is when we plug in 2 into both of these guys. So this is going to be 1/3 here, minus, and then plugging in 2 here, 1/5. The third term in the series is going to be plugging in 3 here, so that's 1/5. And also plugging in 3 here, so that's going to be 1/7. And it's just going to go on and on like this. But let's again look at it as a sequence of partial sums. So if I look at the sequence of partial sums, this would be the first term in my sequence of partial sums, which is the first term, 1 minus 1/3. But the second term in my sequence of partial sums is the sum of these two guys. Now you can see that when I add these two together here, right? In fact, I'll write it this way. It's basically this 1 minus 1/3 plus 1/3 minus 1/5. And we'll come back to that in a second. The third term of the sequence of partial sums is going to be the sum of these three. So that's 1 minus 1/3 plus 1/3 minus 1/5 plus 1/5 minus 1/7. So that's the sum of the first three terms right here. And eventually we'll get to a general term for the sequence of partial sums. But something interesting is happening here, right? The negative 1/3 and the positive 1/3 cancel here. So the second term in my sequence of partial sums is 1 minus 1/5. Here, of course, these cancel and these cancel. So the third term in my sequence of partial sums is 1 minus 1/7. And we can list these as the sequence of partial sums. So I'll write it up here. The sequence of partial sums here, what does it look like? Well, the first term is 1 minus 1/3. This is a sequence, right? So that's the first term is 1 minus 1/3. The next term is 1 minus 1/5. The next term in this sequence is 1 minus 1/7. And so on. So what would the general term in this sequence be? Well, when n is 1, we have 1 minus 1 over 3. When n is 2, we have 1 minus 1 over 5. When n is 3, we have 1 minus 1 over 7. So that's not quite 2n, but it is 1 more than 2n. So it looks like the denominator is going to be 2n plus 1. So my general term in my sequence of partial sums is going to be 1 minus 1 over 2n plus 1. So we have this sequence, right? These are commas here separating the terms. So we have more terms. The general term, 1 minus 1 over 2n plus 1. And of course we have more terms after that. So that's what the sequence of partial sums looks like. And remember the deal. The deal is, oh, by the way, before we do that, there's a name for this cool thing that's happening here. So what you see happening here with this collapsing of the inner terms, this is called telescoping. So telescoping is what happens when this occurs. These inner terms are collapsing on each other. It's kind of like those telescopes that kind of fold in like this, right? Fold back out, right? Probably familiar with those. That's why it's called telescoping. But what do we want to do? We want to do this. We want to analyze that sequence of partial sums and see, okay, does that sequence of partial sums converge? If so, then my series does also. So does the sequence of partial sums converge? Well, we know this if we can look at the infinitieth term of the sequence of partial sums. So that would be the limit as n goes to infinity of s sub n, because I want to see that infinitieth term of the sequence. So we do it. This is the limit as n goes to infinity, and thankfully we came up with a expression for that general term for the sequence of partial sums, and it's this, 1 minus 1 over 2n plus 1. And of course, as n goes to infinity, this approaches 0, so this expression is approaching 1. So the limit as n goes to infinity of s sub n is equal to 1. Since the sequence of partial sums converges, the series also converges. And not only that, the series converges to 1. So I won't write all that here. We would if we were doing it for real, but that's what's happening here. So we analyzed it with a sequence of partial sums 2 different ways, but this one introduced that idea of telescoping, the collapsing of those inner terms. But if the sequence of partial sums converges to 1, that means the series does also. Okay, finally we'll take a look at this series in the calculator so we can really see what's going on with it. Next. Okay, so here I am in the calculator, and I'm going to analyze the series we've been looking at, the series which is the sum from n equals 1 to infinity of 2 over 4n squared minus 1. So I'm going to enter it in the calculator here. So 2 divided by 4n squared minus 1. Okay, and the variable here is n. We're going to start when n is 1. We'd like to end when n is infinity, but let's just go to 100. That's good enough. The step size is 1 because we're indexing by 1, right? N is 1, then n is 2, and n is 3, so on. Okay, so I'm going to paste this into L1, and here's what it's giving me. So these are the terms that make up the series, right? The first one is 2/3, the next one 2/15. That's this number, and then the next number is this. So when we set up the series, right, that is the sum of all of these numbers right here. You can see that they are getting smaller, and we know that they're approaching 0. And it turns out that this converges, this particular series, when we add them up. So now what I'm going to do is I'm going to go over to L2, and I'm going to find the cumulative sum. So I got to find that button in here. There it is, choice 6. So I'm going to do the cumulative sum of the numbers in L1. And remember, what the calculator is doing here is it's actually giving you the sequence of partial sums. So there's the first term. This 0.8 is the sum of the first 2 if we added these 2 together. And then this is if we add the first 3 together. This is if we add the first 4, and so on. And as we scroll down the list, we can see that we're approaching 1 eventually, right? So I probably should have gone further than 100, but you get the idea. We're approaching 1 eventually. So we are converging to 1, as we can see here with the calculator. So by the time we get to the 100th term, we're up to a sum of 0.995, I guess, right? So that's our sequence of partial sums, which is the first number is 2/3, the next number is 4/5, this is 6/7, that's 8/9, and so on. By the way, one other thing I'd like to show you is, here's the sequence of partial sums, right? This is 1 minus 1/3 right here. That's 1 minus 1/5 right there. 1 minus 1/7, 1 minus 1/9, and so on, right? So that's our sequence of partial sums. And again, if your sequence of partial sums converges, that means your series converges to that very same number.